Hi, and welcome to 7.4 lecture on Freefall. So the first thing I want to talk about is a little bit of an introduction to what Freefall is. So the first thing that we want to talk about is, does a heavy object fall faster than a light object? So I've got two objects here. We're going to call this one on the left. Let's have this one as a heavy object and this one as a light one. Which one falls quicker in a gravitational field assuming no air resistance? And that was a question that Galileo Galilei, who was alive between 1564 to 1642, wanted to answer. Now, he was the first one to discover that actually it doesn't matter. Whatever the mass of an object, they will fall at exactly the same rate. And the way he did this is, he was alive, obviously, before the invention of stopwatches or clocks or anything like that. So how did you do it? Well, actually, he put these balls on an inclined plane and timed how long it would take them to roll down. But how did he time? Well, he timed them using a water tank which dripped some water out, and he calculated that the balls were accelerating down because they were covering a larger distance per each drop of water. So that's how he did it. But the way that we do it now, and indeed some of you may already have done it, is by dropping a little ball bearing. The way that we would measure the acceleration in a lab is we would drop a ball bearing and we would drop it through a known height that we might call S, and we would drop it from a known velocity that we might call U, and we would use some clever technology to get the time, T, and we would put that into a Suvat equation. So we would have S, U, V and A and T. So if we knew what S was, we knew what U was, and we knew what T was, then we could work out what A is. Now, something to note here, if we are starting at the top here, moving downwards, and our acceleration is downwards, it makes sense for our positive direction to be down. So our equation that we use, we've got S, we've got U, we have T, and we have A. The equation that we would want to use is S equals UT plus a half AT squared. And this is the equation that would govern our freefall. Now I'm just going to pause there for a second, and I want to show you a quick video, a quick proof of what Galileo was saying. So let's just hop onto YouTube for a second, and let's just see what they found.
Wind and penetrometer drum in the ETD.
We're dropping a hammer and a feather at the same time.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. Oh, wow, watch this. Joe, you have a good picture there. I've got
Beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? Proves that Mr. Galileo was correct. And
So what we see there is that we've got a hammer. That's my hammer. I can't draw a hammer. And that's more like a banana. That's my feather. And that's my feather. And they're dropping at exactly the same, and they're dropping them on the moon, and they hit the ground at exactly the same time. Now, if we tried that on Earth, that wouldn't happen. That wouldn't happen on Earth. So on Earth, wouldn't happen on the moon. That does happen. They do drop at exactly the same time. Why doesn't it happen on Earth? Because of air resistance. Now that's something that we'll come on to talk about in a later topic of forces. But what I really want to speak about today is what happens here. So I'm just going to move on, and we're going to take our equation S equals UT plus a half AT squared. Now, if you remember, if we had SUVAT, our U was 0 because we were dropping the ball bearing and it was starting from an initial velocity of 0. So our equation becomes, we can cross that out, becomes S equals a half AT squared. Now, if we want to find what A is from here, there's a couple of ways you can do it. But the best way is to notice that this equation looks a bit like y equals mx. And then we can map our s onto y, our t squared onto x, and our half a becomes our gradient. So if you were to plot a graph of your s values on the y-axis and your t squared values on the x-axis, you should get roughly a straight line through the origin, the gradient of which must be equal to a half a. And if you did the required practical, that's what you found. You found that your gradient was equal to a half a. So, we can look at the example from the book on page 127. So it says a coin was released at rest at the top of a well. So it took 1.6 seconds to hit the bottom of the well. Calculate the distance fallen by the coin and its time and its velocity just before impact. Let's say that again. A coin was released at rest at the top of a well. So here's our well. Coin was released at rest at the top of a well. Released from rest. That tells us U equals 0. And it took 1.6 seconds to hit the bottom of the well. Calculate the distance fallen. So, well, we know acceleration has to be equal to g. Let's set our positive direction as downwards. So we can have it as 9.81. And let's write out what we've got. So we can use s equals ut plus a half at squared. And we know that s must be equal to 0 times 1.6 plus a half times 9.81 times 1.6 squared. So therefore that goes s equals 0.5 times 9.81 times 1.6 squared, which equals 12.5 metres. That means the well is 12.5 metres deep, and we can go back to the top and put in s equals 12.5 metres. And now it's asking for the final velocity. Now, it's always a good idea not to use values that you've already calculated in your calculations for something else. So we want to find v, and we can use v equals u plus at without using s. We know u is 0, so v equals 9.81 times 1.6, and that equals 15.7 meters per second. So this concludes our mini lecture on Freefall. I will be uploading the summary questions as well. Please feel free to comment if there's any questions that you have. Thank you.